Hey, welcome back. It has only been 10 months since I put out the video on the Deckel FP1 high-speed head, where I did a teardown and disassembly of the entire mill head. And I think it's finally time to put this back together and into service, so it's not taking up valuable bench space anymore. To give you a rough idea about the timeline, I tore it down and cleaned everything 10 months ago when I put out the video, but right after it I put it back together for the most part and also filmed it. But when I put the Quill assembly back together and the bearings, so unfortunately that's one of the most interesting parts, I lost quite a bit of audio due to sheer incompetence on my end. I simply forgot to turn on the wireless microphone, so this part of the video will unfortunately be voiceover. I'm sorry for that. I would prefer it to be my regular audio commentary right in the video, not voiced over. Before I'm reassembling the spindle, I'm cleaning all the components. Here I'm using some semi-chrome polishing compound and some WD-40 for cleaning. The semi-chrome is a super mild abrasive. If you put it on a rag or a piece of paper towel, it's great for cleaning off baked-in dirt or surface discoloration. It's just very, very mild. WD-40 and an old toothbrush to clean out all the excess dirt and the polishing compound from the gear teeth for the Quill drive. This is a stage where you can use pretty much everything because there are no assembled components. You can use solvents, brushes and compressed air as you desire. Once it's assembled, you have to be very careful with what you use. With solvents, you can wash dirt into bearings. With compressed air, you can blow dirt into assembled bearings or sliding fits and create quite a problem. Same procedure on the inside of the spindle, cleaning out the bore. Here I'm using only WD-40, no abrasive, because there's also the bearing races for the lower spindle bearing. For the time being, I'm putting the Quill into a plastic bag so it doesn't collect dirt from me working here on the bench. Thorough cleaning of the spindle, make sure there is no dirt in any of the sharp corners of the spline drive. That's a close look at the bearing race that's ground into the spindle. Taking a close look at all the bearing balls and also the bearing cage. For the bearing cage, you have to be careful. It's a little bit fragile since it's made of linen reinforced phenolic. But still, all these components need to be very, very clean. You cannot have any dirt or dust on the cage or the bearing balls. Don't put them in a ultrasonic cleaner. If they touch each other in their ultrasonic cleaner, they will damage each other. Putting the bearing components away until time for assembly comes. Stoning the preload nut. Looking for any high spots where material has been raised, like around the spanner holes or the radial threads for the lock screws. As you can see, I'm marking some high spots where material has bulged out from torquing the set screws. Preparing for assembling the spindle, cleaning of the workbench so it's as clean as possible when I work there. Putting down some tin foil. This is a nice and clean work surface. A quick look into the manual for the high-speed head, which has lubrication instructions. Every 5,000 hours you have to disassemble the spindle bearings. Clean everything and reassemble with Kluber Isoflex Supertel. Nobody ever does the 5,000 hour disassemble and reassembly. Reassembling the front spindle bearing. I have a dab of the Isoflex grease in the Petri dish to the left in the image, and I'm dunking each of the bearing balls into the grease. And this is not only the lubrication, but it also helps me to assemble the bearing because the bearing balls don't fall out of the cage anymore. That way I can easily put it all together and this will be fine. These spindle bearings do not get very much grease. As mentioned in the manual, you just coat it very lightly with the grease, otherwise you will get trouble with heat. Dropping the quill housing on top of the bearing. Very carefully to not knock the balls out of alignment. And yeah, that's the correct assembly here. Time to the rear bearing. Reassembling the rear bearing is a little bit tricky because you do not have as much space to work with. You have to get the balls between the spindle and the quill housing, but with a little bit of grease for both lubrication and assembly, it's not a big of a deal. Make sure they're all sitting nicely there. Now we can assemble this rear bearing race. This is what adjusts the end play in the bearing. It has a very tight fit on the spindle and has the rear bearing races ground into it. But usually you should be able to put it on by hand without needing a press. At least far enough so the adjustment nut gets into engagement. Next we have bell wheel washer and the adjusting nut for the spindle. This adjusts the end play and the preload in the bearings. The correct preload is stated in the manual. Spindle should have less than 3 micron of end play axially, and at the same time the bell wheel washers shall be able to be moved by hand ever so slightly. So that's also the indication that you do not over tighten it. I just noticed that I recorded half of this video without audio because I didn't turn on the audio receiver on the camera. Thank you for nothing. So I have the electronic indicator out, the MAR Millitron. It's set to 0.530 range, which is the black scale, which is the upper one, from 0 to 3, but we have to read it as 0 to 30. 30 micron. So 30, 20, 10 micron are the numbered lines. The large lines are 1 micron increments and the smallest lines are 0.5 micron, half a micron. And I have the shortest possible measurement loop here with this small hydraulic indicator stand, which honestly is really good. If I shake on it, there is not too much. I think I touched the indicator. There is not too much going on here. This little H&G indicator stand really is nice. This is a true hydraulic one. And I'm measuring directly against the face of the spindle to check my axial play. So let's push and pull on the spindle and see how much axial play we have. So let's pull here and zero out the electronic indicator. Then I push, then I get almost to 10 micron. Yeah, that's I'm not looking straight onto the instrument, so for you it's probably looking different, but that's pretty much 10 micron. It would be nice if we had something that fits in here as a wrench. So this is returning to 0 when I release the pressure on it. I think we're fine here. Let's check radially. Yeah, I know this. This is the outside of the spindle and this doesn't have anything to say. But even on the outside of the spindle, let's go to finer increment. This is 0.05 micron per smallest division and 3 micron total. So on the outside of the spindle we have now a run out of maximum 1.5 micron. To give me a little bit more help putting this thing together, I'm going to put the drawbar in. At least temporarily. Pipe cleaners are nice to get bores cleaned. That's the pinhole for the drawbar. Pushing the pin in, and I'm just using the Knipex pliers to press it home. So the parallel pliers are sometimes really nice. Okay, let's get the LVDT out of the way, clean the taper, and I have a nice test bar here. In very good condition as far as I know. There we go. That's 140 millimeters away from the spindle nose. Let's see what we get run out wise here and play wise. This is really, really good. I moved the LVDT out a little bit more, the electronic indicator gauge head, to 170 millimeters from the spindle face. The gauge amp here is still set to 10 micron full range, so 0 to 10 on the lower scale, on the green one, and each small line is 0.2 micron. Now let's see what we get here. We get, yeah, this is like 2 micron in this distance to the spindle. 2 or honest 3 microns. Really not a big problem. Let's see what we get side-to-side play-wise. I'm rotating it to a position where I get the needle on 0, and I press down on the test bar. And it goes back to 0. And when I push from the underside, it also goes back to 0. This tells me that all we're measuring here is now me bending the test bar, not exceeding any play or side-to-side play in the bearing arrangement. And the electronic indicator is so sensitive that you need to be careful with the cable. When I touch the cable, the dial, the instrument goes all over the place because the cable is putting so much strain, mechanical strain on the whole setup that your measurement goes all over the place. So you have to keep the cable in a way that it stays put, doesn't put any dynamic load on your setup, just static loading. In some cases you want to zip tie or Velcro tie the cable to the stand, for example, just to strain relieve it. But in overall, gauge amp is really a nice item to have. And with that, I ruined the pricing for gauge amps on eBay. But I think that happened already by Robin. Let's go to the next part. This is the bearing assembly for the belt pulley. And if you remember the last video, there was a nasty burr. I filed it off. I'm using precision ground flatstone, I'm just making sure that the entire circumference of this bearing diameter is smooth and doesn't have any raised anomalies. I have new bearings for it, SKF Explorer 60082 with shields on both sides. And I wonder how we mount them. Maybe we can heat shrink them in place. Let's go to a little bit over 100 degrees. That's usually fine for mounting bearings. Make sure the bearing is clean. I like to put a little bit of oil on when I do a bearing shrink fit. This is a very, very mild press fit on there. When I removed the bearing, it went with some taps with the leather, with the rawhide melted off. I'm going to let this cook for a few minutes. Okay, let's see if we can get this bearing on or if we need to go to the hydraulic press. There we go. That's always exciting. Then we have a spacer ring, I think. I have to check the drawings. I'm not entirely sure about the spacer arrangement. It's like... It's the two Belleville washers. It's this spacer ring here, the outer spacer ring, and now that bearing drops on. Looking at the drawings, I have a problem with this. There is this set of Belleville washers, and this inner ring should be a sliding fit on this diameter here. So let's turn off the hot plate. Otherwise, you cannot adjust the end play of this pulley adjustment. Otherwise, you put it in place and it just stays there. So I think I'm going to put this in the lathe, and there might be some polishing needed. Okay, I think I definitely stoned down all the high spots here. Now this bearing should be I very thoroughly stoned it on the lathe, and now I can assemble it without a problem. Still, I'm going to heat the bearing a little bit, just so it drops on nicely without the problems that I just had over on the lathe. You have this problem very often when you assemble large diameters that are a fairly precise fit. Okay, let's add a little bit of oil again. Add the outer spacer. While the bearing is heating up, just hit this with a stone and make sure it's clean. There is the bearing. There we go. As you can see, this is loose. Now we can push it together until the outer ring hits the spacer, and the Belleville washers on the inside will preload the inner ring. It's quite a nice design. So here is... Let's tighten this nut until the spacer ring. The Belleville washers in there are fairly beefy. Okay, that's a little bit preload. Okay, this is looking good. Now this entire setup here can drop back into the casting, and it's secured with one set screw in the spacer ring. And then we have a very, very precise bearing arrangement for the pulley. I think we're going to heat this with a hot air gun. Okay, hot air gun to heat the casting a little bit. This is going to be one of those funny assembly problems where this hole has to line up with the set screw hole in the casting. And there we go. Set screw for alignment. Now it should pull the spacer ring into position. I think it's time to put the quill back in place. Let's take a little bit of oil, wipe the spindle, the quill bore once again. I had to pull the drawbar, otherwise the quill does not fit through the pulley drive up there. Let's see, there is a key in there, so this needs to be aligned. And also there is a pin that aligns the quill in the casting. Let's see. Oh, this is going to be fun. Uh-oh. From this point I just can take the pinion shaft. Let's see how well this works. There we go. Hello, mad tight fit. Okay, this is still without the quill spring, of course, and this is not lubricated. But the worst part is behind us. Let's get the drawbar back in. Drawbar goes through there. There is a hardened washer. We will put some molybdenum grease on it, just to reduce wear over time, and these drawbars can seize up. Ask me how I know. Run the pipe cleaner through there. Tapered pin from the correct side. Okay. And use the parallel pliers to push it home. So there we go. That's the drawbar installed. I think next would be, I think I'm cleaning this workbench off first. There's a lot of crap that doesn't need to live here currently. Okay, while cleaning all these parts, I noticed that I can pull the return spring or quill spring assembly apart without it exploding, because the spring is not tensioned anymore. Well, I wouldn't pull it out here. It probably would go very much spring on me, but as long as I don't muck around with it, it should be safe. And I can clean this piece here as far as I want. This side of the spring has a loop bent onto it, and the housing has a hole drilled here, and this hook engages into this hole. Okay, that's back in there. spring housing goes on here. Now I can tighten I just wound up the spring for the quill return. Let's see if it's strong enough already. Yeah, that's good. This will get a little bit looser over time. This is 220 weight whey oil in there. It has some drag to it, but this feels very good. I like it. So I'm going to leave the quill setting like that, the spring setting. This was one full rotation on the quill spring. Let's put the clamp back together. This is the lower ring that's actually clamping around the quill. I'm putting all of this together with oil because that's also what we lubricate the quill with. I have the overarm support here. I oiled up the flange and the centering diameter here. Everything is clean. Screws have a tiny dab of molybdenum disulfide grease on them. Let's put it back together. Make sure this flange surface is clean. Same for the diameter that centers it. And it's back on. Okay. Should be able to swivel. Excellent. That's way better than before. You remember how I needed to hammer it off the overarm support. And now it's nice and smooth. I think next piece is already the casting that holds the motor. Some molybdenum disulfide grease on the mating diameter. The aluminum casting. Okay, that's the flange that holds this in place, captive, so it doesn't fall off when you tilt the head to the side. This can spin to the side because in certain orientations the motor might collide with the work or with the machine itself, or when you use the double knuckle adapter, the elbow adapter to create the double swivel head, you also need to be able to rotate the motor in different orientations. There's a lock screw here on the side that pinches the casting, so it stays where you move it. All these parts are really cleaned up very well. This bugger is already getting fairly heavy. If we put the motor on, it's getting to a point where it's really annoying to lift by hand. There's the monstrosity of a motor. This is a let's see, 0.75 kilowatt, 1500 RPM motor. I think the bearings are fine, but we'll put it on an outlet later and see how it behaves under power. And it's stuck. There we go. So this is not the original motor. This is already a rebuilt or replacement motor because the original one is only 0.55 kilowatts. My initial thought that this head might almost be unused is not true. Otherwise they would not have replaced the motor, which is interesting. Not sure why they replaced the motor. Three-phase motors usually are extremely durable and don't tend to burn up without a very good reason. I checked the specs and somebody put a motor on this head that's too slow. That's odd. Either they used it like a normal milling head and they wanted higher torque and lower speed, or this was what they had around, or they just hadn't any clue what they were doing. So this is kind of weird now. I'm not going to put this motor on. First of all, this is a cast iron frame motor, and this weighs a bloody ton. This flange here is cast iron all the way through. I'm going to order a modern motor with an aluminum frame. I'm not sure what's going on here. It's now a few months later. This video is dragging out quite a bit. I'm now absolutely confident that the motor that was on my Highspeed head was a retrofit by somebody for some reason. Either they needed the lower speed and the higher torque, or the original motor burned out and this was all they had as a replacement. This is a massive, super heavy, larger frame-sized motor than the original one. Thanks to a friend, I was able to source the original motor with the original cast iron mounting plate that belongs to the Highspeed head in very good condition. It looks like new. So I will put this cast iron monster here into storage. Unfortunately, since somebody retrofitted this larger motor, this also has a larger shaft. This is a 19mm shaft, and the original motor has a 14mm shaft. So, of course, they bored out the original pulley to fit the larger motor. Now I have to go back to the smaller motor, and well, that's annoying. I'm going to machine a small bushing that I will glue into the bore with Loctite 648, and it will have a new keyway broached into it because the key on the small motor is 5mm and the key on this big one is 6mm. So nothing fits to each other as usual. Little trick that I do for work efficiency is just have a 10mm drill bit in a quick change tool holder. And this is not even a V-block style holder block or something like that. This is just a regular stick tool holder, and I'm I'm just clamping with screws on the shank of the drill so it gets pushed in the corner. And I use this as a starter drill when I need to poke a hole into a piece of stock to follow up with boring bore. That's faster than grabbing a drill from the index, grabbing the drill chuck, or even worse, pulling the tailstock in. This is super efficient in my mind. Now that I have the bushing that will go in the pulley, I have to bore the pulley. Otherwise the sleeve would have a very thin wall and wouldn't allow to have a keyway. I just clamped it in the 6-jaw chuck with the regular jaws, but if you look down here, I'm basically only holding on this narrow ring of material here. It's sitting flush against the back of the chuck, but it's only holding on here, and that's not safe, especially since if I really tighten down on the chuck to get a firm grip, I would just crush this small band of material. So I found a piece of all thread, and I will put it in here. And with the fender washer, it will rest at the bottom of the stepped bore. Now I can put a washer and nut on the other side of the headstock and pull the pulley very firmly against the face here. I have still to be a little bit careful to not crack the pulley when I pull when I pull the pulley towards the chuck face. But it's way more secure to have the additional axial force pulling the pulley in compared to just grabbing on this narrow band of material. That's a very nice sliding fit, perfectly for a glue joint. Still need to cut this to length. I went very easy on the cutting on the pulley with the setup. Despite having the drawbar in there, it's still a little bit on the more sketchy side of things. No need to go all hero on this. I pulled the slotting head out and mounted it to the milling machine to put the 5mm key slot in this bushing, and I have the dial test indicator up here on the indexer to center up the tool to the bushing. Double checking that this is my high spot, sweeping over to the other side. Finding my high spot, or depending on how your brain is working, low spot, 0 over here, and this means that the slotting tool is perfectly in line with the center of rotation of the indexing head now. Also checking the runout of the part. Don't turn on the slotting head now. This would get rather expensive. This is not really critical, but I would like to be everything kind of in line. So this is like 10-20 microns now. This is fine. As it's tradition with slotters or shapers, if possible, crank the machine over by hand to check for collisions. This can save you from a rather expensive experience. That went fairly quick. Of course, it's super overkill to set up the slotting head for one key slot, but I have to justify owning the slotting head, so yeah, that's a good reason to use it. But the result is, of course, very nice. If I didn't have the slotting head, I would just have used the Quill of the milling machine to manually slot this, like I have done in the past on my bench shop milling machine. Over at the bench, I cleaned the key on the sanding plate. And here is the bushing with the key slot. And that's a nice result. Fairly happy with this. And the pulley, yeah, this will all go together quite nicely. Scuffing up the bushing with some 400 grit emery cloth. I'm also dropping into the bore and putting a little bit of a scratch pattern in there. Some acetone. Loctite 648, that's also why I'm wearing the glove. This stuff can cause problems with your skin. Wetting the entire surface with Loctite. And also wetting the entire outside of the bushing with Loctite. This helps to create a full surface bond. And then I like to put a ring of fresh Loctite around the edge of the bore, and the wetted bushing goes in with a little bit of a twist. One smooth motion. And usually this ensures that there is Loctite on most of the surface between the bore and the cylinder, the part you're gluing in. So I'm going to let this cure, and while it cures, I'm going bouldering. Okay, I'm back. The Loctite has cured, and the pulley fits very nicely on the motor shaft. This has to go back on here. This is the adapter plate that mounts to the top of the high-speed head. I think it's time to put this thing back together. This is the Spindle pulley. I'm also using a little bit of molybdenum disulfide grease on here. Not only because of the micro movement between the parts, but also it helps against, well, it helps if I have to take it apart again in future, if it's not all dry against each other. I wonder if I can get this on without heating it. Oh yeah, okay, that was easy. I purchased a new belt because the old one was moldy and cracked. Set screw goes in here, lovely slotted head set screw with a point that pokes against the key in the spindle. So it doesn't transfer any torque over the set screw, of course, it's only holding it in place. All the torque transfer is done via the small key in there. Always keep in mind this is not a high torque. This head is not made for high torque applications. So there is the motor. You need to finagle the belt in around the pulley of the motor. There we go. This is the gib that holds the motor in place. goes on here like this, and this part is quite a cool design. It's casting, and it has two dowels for alignment, but it's hollow dowels and there are springs in there. Like this. And this means when you open the screws that lock the motor in place with the gib is automatically pulled out of engagement and makes moving the motor easier. Quite a nifty little detail. There we go. And we'll put these back in place. Well, I think after about a year, it's coming back together. This is the cover that protects you from touching the belt or getting your glorious long hair entangled in the belt drive. It's supposed to have a hinge, but the hinge had a little happy accident, so I will have to find a piece of piano hinge roughly the same dimensions, and I will use that. But for now I will just straighten it out good enough to use it, because I don't want to run this belt unprotected. The Highspeed head is mounted up on the milling machine, and I plugged it into the control cabinet on the other side of the machine as it was intended by the manufacturer. It has the concept of operation with the Highspeed head is rather well thought out. When you run this motor for the Highspeed spindle, you don't have power feeds, of course. You turn on this motor with a single push button on the back of the cabinet. In reality, the cabinet would be standing next to the machine, but since I'm a little bit space constrained, it's on the other side, so that's not ideal. This button turns on the main motor. Then you don't have power feed, but then you still have the option to turn on the main motor of the milling machine, which spins all the gear train in the column and the horizontal spindle, which you can disengage. It will still turn very slowly, the horizontal spindle, but that's just due to drag from the gear oil. So then you have the main motor of the machine running and the Highspeed head, and you can turn off both at the same time by pushing this button. So I think the overall concept is fairly sound. This is a 6mm 3-flute carbide end mill. This is a roughing geometry with chip breakers, and the material here is a chunk of 70-75 aluminium, high strength aluminium. So let's start with some conservative, like full slotting at 10mm, I guess, running at 4,750 RPM. And a feed rate of 160 millimeters per minute. I think that's all the, well, what do I have to say? It just walks through there. The motor noise didn't change at all. It's nice since it's a very low power spindle, but it's mounted to a very rigid machine. I guess that helps. 10mm, 60 square millimeters of cut cross section. 10mm depth with a 6mm cutter. But everybody is a hero in aluminium, so let's find a piece of steel. I changed the material to a piece of 14301 or 304 stainless, which is notorious to be rather mediocre at machining. Also changed to a carbide 4-flute roughing end mill. I will use some cutting oil because I don't want to ruin this cutter by welding it to the stainless. Also I'm going to hand feed, and also I'm not going to take 10mm depth of cut, but that should be self-explanatory. $2mm depth of cut was nothing. Let's go for 6mm depth of cut, still hand feeding. Well, it wanted to give me trouble because it didn't get the chips out. That's why I used the compressed air. But the spindle itself doesn't seem to care for this amount of material removed. This is 6x6mm, 36 square millimeters of cut cross section. Perfectly fine, full slotting with this head. This is all I will ever ask from this. So I put the HSK adapter into the spindle, and this allows me to use the tooling from my CNC mill in here. So this is a 2.05mm carbide drill. And well, I'm not expecting anything surprising here. So well, it drills a hole. Not sure what to say about this, but yeah, the controls are fine. The Quill on these Deckel mills is a little bit weird. It doesn't give you much feedback, but the movement is very smooth. So I never operated a Bridgeport. I was told that the Quill on the Bridgeports is way nicer for sensitive drilling than the Quill on the Deckel machines. But not having used the Bridgeport ones and having grown up with Deckel mills, well, this works for me. Of course, since it's the same design as the standard mill head, it can do all the same yoga. Hell, it can even do more. Wait a second. So, of course, we have the tilting head. Just like this, or this orientation. This gets interesting when you do slotting with a ball end mill. Now let me demonstrate. With ball end mill, you always have the problem that the center of the ball has 0 surface speed because the diameter gets closer to 0. But if you tilt your spindle, you move the contact point between your cutter and the workpiece to a larger diameter, and that creates way better cutting conditions. That's what modern cam and 5-axis CNC milling machines do when surfacing with ball end mill. They tilt the work or the spindle to get better cutting conditions. But in the olden day, you would also do this on a manual milling machine if you had to do a lot of slotting with ball end mill or something like that. The other thing that this head can do that the normal geared head can't do is you can, since this overarm support here is way longer than the mounting dovetail on the y-axis, you can increase your y-axis travel by quite a bit. Yeah, this looks ridiculous. By doing this, you gain about 220 millimeters of y-axis reach. You still are limited to the 150 millimeter y-axis travel, but by moving the head incrementally, you can machine larger pieces that way. Or if you are working on something with a large volume and you just can't reach with the normal head, this will help you too. For the FP2 milling machine, there is a gear-driven spindle head that can be adjusted in a similar way. It sits higher up and it's adjustable by something like 200 millimeters. The only drawback is it's a little bit louder than the normal one, but I think it's the preferable style. Also, you gain C height. I will put a picture on screen of the long reach head for the FP2. I will probably never need this, so let's put it back in something more normal. A drawback I would consider is the additional weight of this head. The longer overarm support and the additional motor and all this stuff here, this adds to the weight on the y-axis ways. Does it matter much? I don't know. I'm not entirely sure what to show you with this high-speed head. It's just a faster spinning spindle. It's a little bit less stiff than the normal geared spindle. It has less power, but basically from the operation and what you would use it for, it's kind of the same, only that you can use smaller cutters a little bit more efficient. 6,000 RPM still is not like competing with modern machining centers. But here, 4mm 2-flute carbide ball end mill, and I'm just going to do a little bit of slotting with it, with the spindle tilted to get a little bit more surface speed on the root of the ball shape. Let's see how it goes. 4,750 RPM and a feed of 160 millimeters per minute. I mean, yeah, it's cutting very nice. The tilting of the spindle for a ball end mill does a lot. I don't know what to say. It cuts nicely. It works. It's running fairly smooth and does what it's supposed to. That's all I have to say about the high-speed head. Thanks for watching. Sorry for the long delay between part 2 and part 1, but the loss in the audio track created quite a dent in my motivation to work on this video. Also, sourcing the motor took a little bit of time, but I hope the end result is still watchable. If you made it this far into the video, you have fallen asleep, or it was at least a little bit enjoyable. Hope you learned something. Thanks for watching, and I'll be back.